Let's start by thinking about the process a number goes through in the Collatz sequence. First, we multiply by 3, then we add 1, then we divide by 2 to the n, where n is the largest value of n that leaves the number an integer, and then we repeat. Think of each of these steps as a triangle. We go from 0 to 1, then 1 to 2, then 2 back to 0. Once the process has completed a full loop, the 3 times a number plus 1, since all multiples of prime integers are at least 2 apart, this number must not be divisible by 3. After we divide out all the 2's, the resulting number must also not be divisible by 2, by the same logic. Next, observe that one input must always lead to the same output. This means that following the sequence from the perspective of any given leg of the triangle is equivalent. For instance, if I input 5, 5 times 3 is always 15, 15 plus 1 is always 16, and 16 is always a 2 to the n. Going back from 5, we could have been at 5 times 2 to the third, because 5 times 2 to the third minus 1 is divisible by a single 3, which is to say 5 times 2 to the third always leads to 2 to the fourth, or 16. And 5 times 2 to the third minus 1 always leads to 5 times 3. Because the process resolves forwards, and because every step of the process going forwards has only a single possible outcome, we can ignore any 2 legs of the triangle that we would like to. I will call this the no evens, no threes Collatz world, but for the purposes of the proof, I will only refer to this as the world that we are in. Next, let's think about this going forward idea. We can also go backwards, as I just showed. Let's rename the ideas of going forwards and going backwards to ancestors and descendants. That is to say, when we go forwards from a number, I'm going to represent that next number as a descendant. And if we would go backwards from a number, then I'm going to represent that as an ancestor. The rule for ancestorship is take a number in our world, multiply it by a power of 2, subtract 1, and see if that number is divisible by a single 3. If it is, then it is an ancestor. All numbers in our new world have infinitely many ancestors. This is important, so we need to prove it. Take 3 plus 9x. We can remove 3 from both numbers, getting 3 times 1 plus 3x. 3 times 1 plus 3x must be divisible by a single 3 because the inside will always not be divisible by 3 using the same logic from before. However, we also need our number to not be divisible by 2, so we need to multiply 3x by 2 so that the plus 1 will also not be divisible by 2 either. So we have 3 times 1 plus 6x. Multiplying this back out, we get to 3 plus 18x. All the logic we just used also works with minus 3, or 3 times minus 1 plus 3x, which leaves us with 18x plus 3, and 18x minus 3 will always be divisible by a single 3. Therefore, we have proven that 2/9 of all numbers are divisible by a single 3, and that these are evenly spread out across the number line. Now we need to prove that in our ancestor relationship, we will always be able to find these spaced out single divisible by 3's. 2 to the n mod 3 is never equal to 0 because 2 and 3 are both prime. So 2 to the n mod 3 is equal to 1 or 2. Now as we multiply by 2 to the n, as in we keep multiplying by 2, this outcome just keeps multiplying by 2. In a future video, I will explain exactly how the equal sign works with modulus, but for now, just take it on faith that we can use the equal sign as an equation, given that we are doing multiplication, subtraction, or addition. So when we have 2 to the n mod 3 is equal to 1, then we can just times by 2 to get 2, and then we can times by 2 again to get back to 1, because 4 minus 3 is 1. Therefore, any number that we have which has a prime factorization, meaning 2 to the n times some prime factorization that we start from, which all numbers must have, either mod 3 is equal to 1 or mod 3 is equal to 2. And so then they just flip back and forth between 1 and 2 as we multiply up through 2 to the n. When 2 to the n mod 3 is equal to 1, then the minus 1 after we do the subtraction must be divisible by 3. And so as we check for ancestral relationships, every time we check, exactly half of them will be divisible by 3 and the other half won't be. And they will flip back and forth between divisible by 3 and not. But just because there are infinite divide by 3's doesn't mean there's infinite divide by a single 3's. we need to repeat this, but with 2 to the n times p mod 18, where again p is the prime factorization of the number that we're checking for ancestors from. And this can be any Collatz number in our world. Since we have declared that in our world the p in the prime factorization must not contain 2's or 3's, that means initially from this prime factorization we must not be able to start from anything that has the same divisibility of 18. Okay, so let's just check every possible modular relationship as we multiply infinite 2's. 0 has actually already been covered by the idea that 2 and 3 can't be divisible. That's because if p mod 18 is equal to 0, but 18 is divisible by 2 and 3, and we know that the prime factorization of our number in our world cannot contain 2's and 3's. So 0 is also eliminated. So let's start at 1. 1 goes to 2, which goes to 4, which goes to 8, which goes to 16, which goes to 14, which goes to 10, which goes back to 2. This then forms an infinite loop. We have proven previously that relative to 18, when a number mod 18 is equal to either 3 or 15, then they must be divisible by a single 3. Therefore, in this infinite loop, every time we reach the number 4 or the number 16, then when we do the subtraction by 1, the resulting number must be exactly divisible by a single 3, and therefore a valid ancestor. So when we start mod 18 is equal to 1, we know that there will be infinite ancestors of such a prime factorization. Now let's talk about 2. Well, we eliminated all numbers divisible by 2 already. Now let's do the number 3. Well, we also eliminated all numbers divisible by 3, so 3 is out as well. Next, 4 is divisible by 2. Then 5 becomes the next number we have to check. 5 goes to 10, but 10 is in this main loop. Therefore, 5 ends up in this infinite loop that has infinite ancestors. Next, we check 6. 6 is divisible by both 2 and 3. Then we have to check 7. 7 goes to 14, which goes to 10. But once again, 10 is in the main loop, and so we know that it will also have infinite ancestors, just like 5. 8 is divisible by 2, 9 is divisible by 3, then 10 we know is in the main loop itself, and so we don't have to check it. Then 11. 11 goes to 4. 4 is in the main loop, so any number mod 18 that is equal to 11 will have infinite ancestors. 12 is divisible by 2. 13 goes to 8. 8 is also in the main loop. 14 is divisible by 2. 15 is divisible by 3. 16 is divisible by 2. And 17 goes to 16, and 16 is in the main loop. 17 was the last number we had to check, therefore we can be absolutely certain that no matter what prime in our Collatz world that we choose, all of them will enter this main loop that has infinite ancestors, which proves our initial claim that all of our numbers in our Collatz world have infinite ancestors. Now we are ready to consider the Collatz conjecture fully. I conjecture that all numbers are the ancestor of the number 1. Unlike what I was just talking about, I don't mean that they are immediate ancestors. This statement is true if 3 things can be proven. Statement 1 is that 1 is the only number who is its own descendant. Statement 2, no loops exist, connected or unconnected. Statement 3, no infinite unconnected strings exist, which I will be calling chains. For the sake of clarity, connected means being an ancestor of 1, and unconnected being not an ancestor of 1. When we add 1 in 3x plus 1, the number that follows cannot share any prime factors with x by our prior logic. Therefore, dividing by 2 to the n also shares no factors. Therefore, if a number were its own descendant, it must have no prime factors. There is only one number who is an integer like this, the number 1. Now we may check this single case to confirm, and it is. Proof of statement 2. Take a number in our space, times 3, add 1, divide out all the 2's. We're going to represent this like 3x plus 1 over 2 to the n. For a loop to form, this continued process as a ratio must equal exactly 1 to get back where we started. 3 times 3x plus 1 over 2 to the n plus 1 over 2 to the z is equal to 9x plus 3 over 2 to the n plus z plus 1 over 2 to the z, which is equal to 9x plus 3 divided by 2 to the n plus z plus 2 to the n over 2 to the n plus z, which is then equal to 9x plus 3 plus 2 to the n over 2 to the n plus z. All of these outcomes have 2 to the x in the denominators, and so will the recursive process if we apply the same logic over and over and over again. So, for the ratio to be equal to 1, the top must be some 2 to the n, because the denominator is some 2 to the n. 1, like we just proved, is the only 2 to the n who is odd, so 1 is the only possible loop. Proof of statement 3. An infinite unconnected string who has no loops, such a chain could possibly exist in 3 different forms. A chain that goes on to infinity in both directions, a chain that has a fixed start but no end, and an inverse of the previous, a chain that has an end but no start. Chain 2 doesn't exist because it doesn't have infinite ancestors, but we proved that every number must have infinite ancestors, so it can't exist. Chain 3 can't exist because we can always apply 3x plus 1 over 2 to the n to a number and receive a new number. This fact is not so easy to prove. Observe that humanity has checked up to some number of numbers for convergence to 1. For this to be true then, it must then be the case that our chain must not extend below that region of numbers we've checked. This means that the chain must be generally increasing in both directions, because if it were generally decreasing, it would run into this region of numbers that we've checked. Alternatively, such a chain cannot remain within a range of numbers because it is infinite, and there are no loops like I proved, which means it would consume the entire range of numbers that you tried to bind it to. However, the problem with this last option, the chain is infinitely generally increasing, is that ancestor-wise, it would then be infinitely generally decreasing, and thus, by the same logic from before, it would run into the numbers that we've already checked. There is only one way to resolve this, and that's with a V-shape. Previously, I proved all numbers have infinite ancestors, but each of those numbers also, too, has their own set of infinite ancestors. This diagram is showing an expansion of this idea, where 2, in quotation marks, means the second ancestor of a specific number, whereas 1, in quotation marks, means the first ancestor. These create unique ancestral lines, and we can expand their growth with a simple rule. If it exists on the prior graph, give it its own ancestral line, which means, in quotation marks, 2, and then extend all lines. This picture shows this rule being applied, and here is a literal number example. Start with 5. The first ancestor of 5 is 13. The second ancestor of 5 is 53. The first ancestor of 13 is 17. And the second ancestor of 13 is 277. And we can just keep applying these rules indefinitely. It becomes clear that in such a growth pattern, since it goes on forever in such a manner, eventually one of these lines must get unlucky enough to go below the region humanity has already checked. Or if this is not the case, the inverse of the infinite descendants must be true. But I can't exactly prove this idea, so instead we'll try a different method. First, let me quickly explain modular divisibility. Start with a number, let's say 20, mod 12 is equal to 8. Modular divisibility says that 20 over 2 mod 12 is equal to 8 over 2, which is equal to 10 mod 12 is equal to 4, or 10. Now there is a condition that everything in the equation must be divisible by whatever you're dividing it by. So, in this case, 20, 12, and 8 all need to be divisible by 2. The first answer for 10 mod 12 is equal to 4 or 10 is very straightforward. 4 is simply 8 over 2. But 10 is a little more complicated. First, because we divided by 2, we need to split the mod 12 into 2 pieces. So we do 12 divided by 2, which is equal to 6. Then we add this split onto the first answer we got. So 4 plus 6 is equal to 10, and that's how we get 10. If it were 3, we divide it by 3 and then add it twice. If you want to know which option will be picked, you can read the rule below, but it doesn't matter for the proof. Let's start by asking a question. Could we define an infinite set of immediate increases? This means 3x plus 1 over 2. If so, we would have a candidate for the right half of the v. First, I know that when x mod 12 is equal to 7 or 11, then we may go up. I know this from a similar logic to the mod 18 ancestor math. Now, let's prove it. Valid numbers in our world, not divisible by 2 or 3, when we mod them by 12, are 1, 5, 7, and 11. But unlike before, using modular divisibility, we can prove this very easily. 1 times 3 plus 1 is equal to 4. Then divide by 2 is equal to 2. And then using modular divisibility, plus 6 is equal to 8. But neither of these options, neither 2 nor 8, are valid numbers inside of our world. Therefore, no such number, x mod 12 is equal to 1, can lead to an immediate increase. Here is all of the other numbers worked out. And as you can see, only 7 and 11 are valid. So it is proven that x mod 12 is equal to 7, 11 for immediate increases. But in that math, we can also notice that x mod 12 is equal to 7 times 3 plus 1 over 2 is equal to 11 or 5. But x mod 12 is equal to 11 times 3 plus 1 over 2 is also equal to 11 or 5, which means if we immediately increase forever, it must do so through x mod 12 is equal to 11s. We can use this fact to easily produce such a list of numbers. To get x mod 12 is equal to 11 back to a normal algebraic solution, we can rewrite it as 12x plus 11, where x is an integer from 0 to infinity. We then apply the increase, 12x plus 11 times 3 plus 1 over 2, which then is equal to 18x plus 17. We then know from earlier that this must then be equal to some other y mod 12 is equal to 11, or 12y plus 11. Solve for x, we get x is equal to 12y minus 6 over 18. So then we need to ask the question, what values for y lead to an integer y and x? Well, the list is 2, 5, 8, etc. Or 3z plus 2, where z is an integer from 0 to infinity. Now let's verify that we're right by applying the first number in our infinite list, 2. To get back to the normal numbers, we plug 2 back into 12y plus 11. So we get 2 times 12 plus 11 is equal to 35. Now we can check whether or not this does descend from an immediate increase by taking the ancestral relationship. We do this by saying 35 times 2 minus 1 over 3, and that is equal to 23. 23 is not again divisible by 3, therefore it is a valid immediate ancestor. We can now apply the same exact process again. So we ended up at 18x plus 17, so now let's do it one more time, times 3 plus 1 over 2 is equal to 27x plus 26, which then must be equal to sum 12r plus 11. Solving for x, we get 12r minus 15 over 27. When we solve for what r can equal so that r and x are both integers, we get 8, 17, etc. Or 9q plus 8 for integers where q is an integer from, again, 0 to infinity. It is now very easy to see what the general pattern is. A minimal length of the chain n is q is equal to 3 to the n times m plus 3 to the n minus 1, where m is an integer from 0 to infinity and n is an integer from 1 to infinity, where we then plug this q back into 12q plus 11. Now let's go through an example using this general pattern. Let's arbitrarily pick that we want an 8-length chain. We can then pick any of the infinite options. Let's go with m equals 0 just for convenience. N equals 8 and m equals 0 is 3 to the 8th minus 1. Then times 12 plus 11, and we get 78,731. Let's go back and check if there really are 8 immediate increases ancestrally from this number. 78,731 times 2 minus 1 over 3 is equal to 52,487, which is equal to 34,991, which is equal to 23,327, which is equal to 15,551, which is equal to 10,367, which is equal to 6,911, which is equal to 4,607, which is equal to 3,071, which is equal to 2,047. We can observe this chain was plus 1 longer than expected. This is because the chain may optionally start with an x mod 12 is equal to 7. Thus we have shown our algebraic solution was done correctly, and therefore we can choose an arbitrarily large n to get an arbitrarily large chain of immediate increases. But because we have defined all the values by their integer length, despite their arbitrary largeness, they are still finite. Thus, the v cannot exist of this form. But because we have only relied really upon algebra, and all numbers in consideration are simple integers, any increasing pattern, which the v must have some such increasing pattern, can also be represented algebraically in a similar manner. Let's do another one. Let's pick divide by 2, then divide by 4, which very slowly increases over time. I've gone ahead and done the work, and here's the general pattern. Q is equal to 9 to the n times m plus 9 to the n minus 1, where m goes from 0 to infinity, and n goes from 1 to infinity. M and n both being integers. Plugging all of these numbers back into 12q plus 7. Let's pick n is equal to 4 and m is equal to 0. We get 9 to the 4th minus 1 times 12 plus 7, which is equal to 78,727. Times by 4 minus 1 over 3, and we get 104,969. Times by 2 minus 1 over 3, and we get 69,979. And again we get 93,305, and again we get 62,203, and again we get 82,937, and again we get 55,291, and then 73,721, and then 49,147. But since all chains of minimal length 8 are also of minimal length 7 and 6 and so on, we need to show that they may be filtered according to their length as we were describing earlier. Take, for example, 9 to the n times m plus 9 to the n minus 1. We can observe that if m is equal to 9 to the n minus 1 for the first and m equals 0 for the second, then it must be the case that these two numbers will overlap in their respective lists. As an example, we can choose n is equal to 1 and n is equal to 2, and therefore we get that if we set m is equal to 9 to the second minus 1, which is just 9 to the first, minus 1, which is equal to 8, and m equals 0, then we should find that 9 times 8 plus 9 minus 1 is equal to 9 squared minus 1. And we do find this is true. 80 does equal 80. This is not the only filter one needs to apply, but it is sufficient to show that we can algebraically apply these filters if we wish to refine it down to specific length lists. Therefore, since all such increasing patterns can be described algebraically and then partitioned by their absolute length, despite their arbitrary size, they are all finite. Thus, no such infinite V-shape may exist, as it cannot generally increase, decrease, or remain the same. Therefore, since there are no loops nor unconnected chains, all values in our world must go to 1. But all values not in our world are connected to values in our world, and so they too must go to 1. Therefore, the Collatz conjecture is proven.